Welcome to the first seminar of our seminar series in the Quantitative House. We have some online audiences joining us today. And before we get started, just want to let you know that this seminar is recorded and later on the recording will be posted on our center's website. The moderator today, Kai Chen, Assistant Professor at Yale School of Public Health, and also the Director of Research at the Yale School of Quantitative Health. So it's my great pleasure today to introduce our very first speaker, Dr. Drew Gentner. Dr. Gentner is an associate professor in the Department of Chemical and Environmental Engineering. Also has joined an appointment in the School of Environment. He has his master and Ph.D. from the UC Berkeley, and also he has been at Yale in the Department of Chemical and Environmental Engineering since 2014. His research group focuses on air quality, pollution, emissions, and atmospheric chemistry. His application in both outdoor and indoor environments. And today we are very fortunate to have both Dr. Gentner and also Professor Kenneth Gillingham joining us online. Today, the main topic will be focusing on their recent paper on the climate and health benefits from intensive building energy efficiency improvements. So without further ado, please.
Great. Thank you so much. And my one request of the virtual audience is let me know if you can't hear me clearly. I will try to speak loudly and through a mask, but just chime in if you're having trouble, and I'll stay closer to my computer. All right, so you have both Ken and I here today. Ken wish you could have been here in person, but I get to present this paper that we worked on along with Professor Jordan Peccia up in environmental engineering, a Ph.D. student of mine, Colby Bueller, and a former postdoc of Ken's from the School of the Environment. So this was a cool project that we were really excited about because it was done true interdisciplinary science where I was excited to work with Ken to do some energy modeling and then bring that into looking at outdoor and indoor air quality across the building envelope. And so this brought in some expertise from Professor Peccia and I to look at air pollution and then extend it to the health effects. This fell under the purview of our, hopefully I can click here. All right, of our search center, which Michelle Bell has been the director of up at the School of the Environment, and we're in our last year of the center now. But the overall objectives of this were to look at energy transitions and look at the wide range of sources related to energy production and use in the context of other sources that affect urban air quality and health. And then we paid key attention to both transitions and key modifiable factors. So which things can we change, either through policy or personal choices, so that we can make smarter decisions related to transportation, land use, our power generation and distribution networks. So this had a number of different projects involved with it. Ken's project was number one, and then mine was number two. We were doing this in collaboration with Johns Hopkins, and we had a couple other projects. And so these things were focused on distinctly different areas of air quality, where I was focused more on source characterization and measurements in project two, and Ken was doing a lot of modeling on energy and emissions. And so this project represented in this paper one of a couple things that we were doing as intercenter collaboration within a much larger center structure, and you can check it out online and see a lot of the other great work coming out of Michelle Bell's group and others at Yale, Johns Hopkins, and our partner institutions, which span some co-PIs at Johns Hopkins and other PIs and Dan Esty up at the School of the Environment. So onto this paper. So now it's like dive in and focus. This started, I can actually remember the workshop that Ken and I were at when we were talking about this research question, thinking about how the climate and health benefits intersect when we look at building energy efficiency measures. Because Ken's group was thinking about building energy efficiency scenarios, how we reduce energy use in the building sector to reduce CO2 emissions and affect change for climate mitigation. And I started asking, well, Ken, what about the indoor air quality on that? We're going to drop emissions of pollution outdoors from reduced energy production, but what happens with the building energy efficiency measures? And so thus, this project and this paper was born. As a brief overview of where we're going with this today, we start with the fact that buildings account for 40% of energy usage. That's a lot of our energy demand nationally, so it makes it a really prime target for climate change mitigation and reducing both energy use and associated emissions. These are emissions of not only climate pollutants, but also air pollutants like particulate matter, sulfur dioxide, carbon monoxide, nitrogen oxides. So with these scenarios that I'll show you in a moment, we looked at reductions in energy-related emissions that would be occurring outdoors from power generation, and then translated that to its effects on indoor air quality. And I'll talk about that feedback loop in a moment. But the approach here is to use the Yale NEMS model, which Ken runs up at School of the Environment, to look at energy efficiency scenarios across the entire U.S. housing stock. So we're not just studying one building. We model all the homes in the U.S. and their changes over time with a lot of simulations and a couple models that were interconnected. Then we evaluated the outdoor and indoor air quality implications. So how do the changes in emissions affect exposure and human health, both through outdoor and indoor exposure pathways, and then look at the net effects on human health of these together. So I'll walk through this in a bit more detail, but we start from something where we take a reference scenario, an intermediate energy efficiency scenario just for buildings, an optimistic energy efficiency scenario for buildings, and look at the changes in energy consumption, and then test the carbon pricing scenario for those to see how that affects it. And we'll walk through this a bit more, but if you fast forward all the way, you can see how we will then be able to look at projections in particulate matter emissions from that reduced energy use. So the scenarios, without going into them in great detail, though there's a lot of information in the paper, and Ken would be happy to answer questions, looks at changes in both appliances and equipment and in the building shell. So we have all of this stuff indoors for heating, cooling, cooking, lighting, and other things like refrigeration. And those have a certain amount of energy use with them, and that's been a target of a lot of governmental programs to improve efficiency. You can go and buy Energy Star things. You see them if you go to the store. And so there are targets related to the energy efficiency of those. And then in the building shell is where we start to look at the interconnections at indoor air quality. Because the indoor environment is really complex. The air that gets to us here, or the air in your home, navigates a lot of places, either through a forced air system or just naturally. You have some penetration coming through the walls and some infiltration of air and the pollutants coming in, and some ventilation of the air going out. You may do that on purpose, opening a window, a door, turning on a fan, or that might just be happening naturally, and depending on the age of your home and how well it's sealed, that could be happening at quite a high rate. So we look at the changes in the building shell across a range of environments, and we're going to talk more about residences today because that's where we do spend most of our time, and a lot of our time, and a lot of our PM 2.5 emissions indoors occur in our residences. So we'll look at that, and we'll look at these scenarios where we have existing homes that we look at changes in efficiency that happen at slower incremental rates, and then new homes that are built to the newest specifications, which follow these ambitious but demonstrated improvements. So Ken's model, which is the National Energy Modeling System model, that is the Yale installation of this, and it's the large model developed by the US EIA, covers a whole lot of things in the supply side, conversion side, and demand side of electricity, and integrates it together. So where we're going to focus on today for this paper is looking at the changes in the residential demand and commercial demand that are derived from these use changes in energy efficiency. So if we change the design of a building, we're changing the energy demand there, and that has feedbacks to reduce demand, to reduce production, and thus we have changes in efficiency. So there are a lot of things that are in this model, and if you are a big fan of supplemental information sections and papers, I encourage you to check out the somewhere around 55 pages that exist in the paper, with hopefully every question that you might have about the energy modeling system and Kenneth's other great work using this model. And so if we look at the scenarios, you have the reference case at the top here in red that we play around with the carbon pricing initiative on there. And then we look at the intermediate energy efficiency just for buildings here and see that that drops consumption down somewhat, and a more optimistic one without carbon pricing. The direct effects on carbon dioxide emissions are shown over here, where you can actually see a pretty sizable effect on overall carbon dioxide emissions just from building energy efficiency improvements. So this really points back to that fact that 40% of our energy use occurs in maintaining our buildings and in our buildings. So any change that we make here at a policy level has a pretty sizable effect on energy demand and related climate pollutant emissions. This also has a sizable effect on air pollutant emissions, like criteria pollutants for particulate matter, NOx, SO2, VOCs, some effect on ammonia and carbon dioxide, carbon monoxide, though today we're going to focus mostly on PM 2.5, since that is the driving factor of premature mortality and was the key pollutant of interest for this paper. So here we've defined what the changes are for each of these scenarios over this time horizon extending to 2050 for the energy-related emissions that are occurring outdoors. So if you want to visualize it, what's coming out of the smokestack for PM 2.5 emissions. So that's going to vary a little bit across the country where we generate that power, how we generate it, and so we'll talk about that at the end of the presentation today. So we spend close to 90% of our time indoors. So when we're thinking about exposure to pollutants, we really need to be considering that indoor environment and how it modulates our exposure to pollution coming in from outdoors, but also how it affects how the design of that indoor environment affects our exposure to pollutants that are generated indoors. Now, I wish I had Jordan Petria here with me today so he could answer all of your COVID-related questions related to ventilation and filtration, because that is not my area of expertise. But you can take this emissions term here and think really about whatever pollutant or microbe or anything that you want for your own work, and think about how that's affected by the design of your home or the space that you're currently in. This is a box model. It is actually simplified considerably to just a singular box representing a space indoors. But yes, there's still one equation. For that, I apologize. Ignore the equation if you like. I can try to cover it up. And we can focus on the terms that are used here. So I'm going to point out a few things and how the model connects, just to try to show how this all comes together. So first thing, we have recirculation with a filter. Now here we're predominantly talking about an HVAC system. So forced mechanical air filtration system that you would have in an indoor building. You have it here, your apartment, perhaps up in East Rock, that was built 80, 90 years ago, may not have that, or some newer builds don't have a forced HVAC system. But that is where you would have some active particle filtration that's occurring. Now in the era of thinking about filtering for viruses and other microbes indoors, whether it be COVID or otherwise, we've started to put in some portable air filters. So you could also think about that, but we're predominantly looking at this in terms of the HVAC system. So on the other side here, you have air coming in. So infiltration is that what I was talking about, is coming through the cracks. You have bad window sealing. It's an old building. There's some areas where air just gets in. If it's a newer building, those seals tend to be better and better, and you have fewer spots for air to infiltrate from outdoors. But then you have a penetration factor there for how much particles get through those little cracks. So it gets stuck on the way. It's kind of like a filter, like our Then you have natural ventilation. So you open the window because it's hot out, or you burn toast, and that's going to provide some natural ventilation. Indoors, the main thing is you have emissions. You're cooking, burn toast, or just regular old. You were frying up some eggplant for dinner, and that generated some PM2.5. Number of your appliances while you're cooking actually are pretty sizable PM sources, but that depends a lot on cooking style, and you can be affected by some of the filtration over your stove. We also work into the model the two loss terms of the deposition or the sinks, so particles go to surfaces, and also they can be ventilated outside. But we're thinking today about what is the changes that happen to these terms and how it affects the concentrations indoors. But built within this is thinking about the housing stock. So Colby Bueller, a PhD student in environmental engineering, did a literature review of the U.S. housing stock, working with Peg Long from School of the Environment to determine the filtration flow rates for homes with HVAC and the fraction of homes with HVAC systems, and also the quality of filters in there. If we were all talking about this a couple of years ago, you would probably not be very familiar with the quality of filters that exist up in these systems. But there's this whole rating system for 2, 4, 6, 8, 10, 12, 14, goes up to 16, then we get to the HEPA grades. And that has a major effect on the efficiency of those filters and the filtration of particles indoors or airborne microbes or dust or anything else. And then the infiltration and natural ventilation rates are also affected by home age. So you think about infiltration, home with more cracks, more gaps, has more infiltration through those penetration points. Then the residential energy demand consumption survey was used to determine appliance usage across all homes, so we can look at the distribution in homes. Obviously, it comes down to how many people live in a home, but some of us are cooking all the time. We cook at home every single night. We use the toaster while we're using the stove, while we're using the oven, and some people, will stop by and pick up something from the local waffle shop for dinner most nights. Much to cook. So that's going to have a huge effect on this emissions term, and is going to propagate through this whole system, as you'll see later. So we then model over time the changes in the U.S. housing stock up through 2050 for this analysis, and changes in the building type, which includes the volume of home, sizes are going up, the amount of new homes that are being built, and the characteristics of those homes with respect to the installation of HVAC systems and filter types and all of that. So, and ultimately, the big effect that this has with the changes in the housing stock and energy infiltration or energy efficiency scenario is on this infiltration. So how much ventilation occurs in your home without you actively doing it? You didn't turn on the HVAC system, you didn't necessarily open the window, but you have some pressure changes in home, and the air is also very good at moving through cracks and things, and it will break with it. If any of you just moved to New Haven, wait till a nice cold day, and go stand near a window in an older building, and you'll certainly feel that cool air in some of those gaps. I know I had experience when I first moved to New Haven. So, we also look at the changes in the appliance type throughout the study. I'm going to talk about something I won't refer to it as a Monte Carlo analysis over and over again, but I want to make the point that to constrain the uncertainty in the study, Colby Buehler ran this a lot of times, thousands upon thousands across the entire U.S. housing stock. So if you go through and you simulate a whole bunch of homes with this model, and you look at all the different conditions you can have, what is the net outcome of those? So again, we're not just talking about one home with one set of conditions or a small perturbation study. We'll look at one or two things, but trying to put those all together so we can look at sensitivity to these different features. Reports of the HVAC system, what are the indoor emissions, and how does infiltration change with energy efficiency measures and the age of a home. So, questions before we start moving on to results? If not, good work. You just got through like lecture 5 or 6 of my class on box models. So, you're doing great.
I do have, yes. Yeah, how confident are you in modeling how the housing stock will change, also changes in appliance type out to 2050, or did you use different scenarios?
So actually, Ken, I'll let you answer that one. It's phone a friend time already. The question was, how confident are we in the changes of the housing stock and appliance shifting over time, and how are those scenarios modeled, or are there multiple scenarios in the NEMS model?
That's a great question. What we do is we use, it's built into NEMS, and NEMS explicitly is modeling housing stock changes based on trends in the past. We easily could do uncertainty analyses over those numbers. I think the kind of main takeaway on that from my understanding is that those aren't going to be the driving forces of our final results. Unless you are really dramatically changing the housing stock. And I know this from another paper, not this paper. You'd have to really dramatically change the kind of core housing stock itself. And the reason for this is that there's a lot of inertia in the housing stock. So there may be changes in how well it's insulated and broader retrofits and how they're done. But the basic stock itself is quite slow moving. That said, I think you should take anything out to 2050 with a grain of salt, maybe a very large one. And so I'm not going to hang my hat on the exact numbers on the nature of the housing stock, because it's the full nature of the housing stock that's being modeled. And I'm not going to hang my hat on the full nature of the housing stock in 2050. But I'm pretty confident that the numbers are going to be pretty close to right in 2030, 2035, in that range, and maybe even out to 2040, just because of how much inertia there is in the housing stock. But only a small amount of turnover actually occurs.
Just on the second part, though, I'd have to be more concerned about appliance type. It seems like, we have possible scenarios of complete electrification, right, by 2050 versus not doing that and still having a substantial number of gas stoves, for example, which it seems would have a large effect on your conclusions about health effects. So
the question is on the changes in appliance type, Ken, and I'll take a quick shot at it and let you add to it. But that does get discussed in the paper. We don't include specific perturbations, but we talk about how stoves changing to full electrification could affect that. We get into some really interesting questions then about where are the emissions coming from. Are they derived from the use of natural gas, or are they derived from the process itself? If your toaster is generating PM based on what you're doing with it, not so much based on how much power. Obviously, it's not a natural gas toaster. But we're thinking about a stove, some fraction of that PM comes from the actual burn itself. But if it's a reasonable stove, the PM is probably coming more from the cooking itself. And that's a really interesting question, and one that there was a cool paper that came out of Stanford looking at the emission rates, although they were thinking more about that thing in particular, which is where you have a huge impact on medical compliance electrification effect. So on the climate side is where I think we can see a large effect of short-lived climate pollutants there. And we do build in a few scenarios in there to look at some of these changes and try to bound them. Ken, can you grade my response and add anything to help there?
I like your response. I want to add a few things. One thing is this paper is explicitly about improving the efficiency given the existing forecasted technologies in NEMS. In our scenarios, it's not about fuel switching, and I think fuel switching is a really, really important question. And we actually have work underway to explore that question, where we're looking at scenarios that actually would allow fuel switching. So, say switching from burning natural gas in your range to an induction range, right? Electric induction range. So that type of fuel switching, we hold constant in this. So we don't, any trends that are in the baseline in NEMS, we continue and we don't focus on those. Our scenarios are very much about improving the efficiency. I think in reality, you may end up seeing both happening somewhat at the same time, but it depends on the policy direction. You could see a world in which you do see a lot of fuel switching and not much efficiency, or vice versa. And I think from an intellectual perspective, it's really helpful to parse those out and understand them separately. So that was sort of some of the thinking behind it, how it plays out in what we do here in this analysis. But it's a really great question and a really important point that I think is becoming increasingly important as we move forward because of the IRA, the recent act and other efforts to lead to electrifying the home. There's been a real push in that direction. So I think, but this framework that we've set up is reasonably well suited with some modifications to understanding the implications of some of those questions too.
Thank you for the questions. Just so I don't have to skip slides at the end, I'm going to move forward. Yuan, to answer your question, the exact materials that are used to change the building efficiency in terms of insulation are not explicitly worked in here, but they are part of changes in building shell efficiency. And so we look at, in the paper, we discuss how changes in insulation versus changes in building ceiling could affect the ultimate outcome. All right, so participation time. How many people in the room have an HVAC system in their home or apartment? Okay, so we're talking. All right, so that number came in at about 10%. I don't know, hands are really kind of low on there. So now is where we have like a choose your own adventure moment in the presentation. So for those who are in homes that do not have, it's going to come back, I promise. All right. Recirculation with filtration. Here are the overall results for the entire U.S. housing stock. Comparing the reference scenario here in the reddish-orange color to the intermediate case in blue, and then green is the optimistic energy efficiency case for buildings. On the bottom here, you're looking at the indoor emissions percentile. So the far left, this is the person who picked up falafel for dinner every night there. Hopefully they got different toppings, but they did not do much cooking in their home. At breakfast, they got on the way to campus. And on the far right here, this is the person who wanted deep fried cauliflower 3 times that week and is cooking a lot. Maybe it wasn't deep fried cauliflower, but you get the point. Here is where there's a lot more indoor emissions. So it's what you could imagine a home that has more PM generated from various appliances, but cooking ends up being an important one. And on the far left is what you could think of as a cleaner home, just in terms of the indoor emissions. So if you're all the way here on the left side, you're seeing actually a benefit compared to the reference case of building Titan. So reducing that infiltration actually yields you a benefit. And the reason is any of the PM that is outside is not making it indoors because your home is sealed off. You have a tighter box that you live in. So you are just living with your own emissions and you don't have as much infiltration of particles from outside. If you move to this other side here, and you can see where it is worse than the, this is with recirculation. I said before this was without. This is for the 10% of you that have an HVAC system. Here on this side is showing if you're doing a lot of cooking indoors, you actually see a penalty from those energy efficiency measures. Because now you have bottled up your home, you have filled all the cracks, maybe not every last one of them, but you have improved the ceiling through your home to the point that you spend a longer time with any of your emissions indoors. So the bummer is that toast that you burnt lingers longer, or any other combustion source that you have indoors, and so thus you would have more exposure to that. Or it could be a continued source of something. If you had a bad pilot light or something else in your home, then that would persist along. So when you're looking at this, the reference case models the building stock without any changes from the energy efficiency scenario. So what is the current inertia and everything that we talked about. And then this represents the change, where the left shows some benefit and the right, where you get above the reference case line, shows a detriment indoors. So for those of you, the 90% in the room that don't have an HVAC system or other recirculation with filtration, this is what it looks like. So everything is the same here. The only difference is now we're looking at the 38 to 45% of homes, depending on the scenario, that have no filtration or HVAC system in the home. So now you can see this effect is exacerbated. There's a smaller fraction of homes that see a benefit for their indoor pollution from these energy efficiency measures, and a larger fraction that get greater exposure to particulate matter because they spend more time with those emissions. So this shows two things: the importance of the indoor emissions in determining your indoor exposure and targeted ventilation there, and the importance of recirculation with filtration just for PM 2.5. Yes.
This might be a silly question, but it's hard for me to understand how building efficiency has that much of an impact over like HVAC. Like I would think that homes that have this circulation system would be filtering air more than like having cracks in the wall, and like not as great of efficiency would be would like have an impact on this. Does that make sense? Like just looking at the reference line there. Mm-hmm. So like if there were no improved efficiency in the building, you would still be having this kind of like being close to the 1-to-1 line if you had a lot of indoor air emissions. But then you improved like how is the HVAC not filtering? I just think of it as like constantly pulling air out and like pushing fresher air back in. So how is the increased efficiency of a building making that almost worse? Does that make sense?
It does, and it's actually a great opportunity to make a clarifying point here that in the current paradigm of building temperature, climate control, and filtration, this is a closed loop. Your HVAC system takes air, conditions it, and puts it back in your home. So it comes down to the efficiency of that filter, rather than it saying, "Oh, we're going to give you completely fresh air from outside, get rid of all your air from inside, put it outdoors." This is where we be thinking about like next generation things. Is there any opportunities to get fresh air while not paying the penalty for having to completely recondition. When I say recondition, I can change the temperature for all the air coming in. Okay. No problem. That's a good point to clarify. So thank you for that. The only major everyday example for a lot of us, or exemption to that, would be in some of our labs. We have a fume hood, obviously, we dump all of that out of the building. We don't recirculate that. And there were some changes in various buildings, like on campus, I know, where the percentage of fresh air versus recycled air was changed over the past couple of years. So, all right. So, yeah, if we think about this effect, this is looking at the overall effect, the entire U.S. housing stock for these two cases, or two types of homes across old and existing. Then we have this result where we end up at steady state, having higher overall concentrations. If you want to visualize this more as what's happening for any singular event, you can think about the response time to something. So if you just look at this as a singular case, let's say here you, we'll stick with the burning toast scenario. You burn toast, or you were frying something, you generated really high concentrations, and then you stopped. How long does that take to decay down? And specifically, we think about that as the folding time, so down to 1/E of 37%. And so we look at that in the different scenarios with and without filtration. One other point, actually, I wanted to make about your quick filtration question is in a lot of homes, we're not recirculating air at a rate of like the entire house every 6 minutes or something. During COVID, we increased some of those ventilation rates for public spaces, targeting air exchange rate of 4 or 5 was what the goal was. So air exchange per hour, but we're not changing everything. So that's why there are some differences here is with the filtration and recirculation for it dropping it quicker in the cases of having an HVAC system. And then you can see, as we tighten up the building more and more in the domestic energy efficiency case, that time that you're spent with the burning of your toast or whatever else that happened indoors increases, and you can see here we're approaching up to twice as long. So that helps to visualize what's happening just in terms of the time. Hopefully that's a useful comparison. So, but we know that the system is sensitive to outdoor PM concentration. So we did all this modeling. And then we did a couple case studies within it across all different outdoor PM concentrations and looked at how the system responded to outdoor PM. Because if we go back to that box model, and I won't put it back on the screen again, but remember we have the concentrations of PM outside, that's trying to come in, and then we have our indoor PM, and that's going out. So we have this really complex game that's happening over the building. And so if we keep our indoor emissions on the bottom, so again, this is the home with the most indoor emissions, this is the home with the least, and we look at the outdoor concentrations on the y-axis here. So this is the ambient outdoor PM 2.5 concentration. The national average is here, the annual standard is here, and then the 24-hour standard is up here. So depending on where you live and even time of year, or if it's a pollution event, you're going to fall on different spots. This graph vertically, and that ratio of what it is in the optimistic energy efficiency case versus the reference case is shown here, where red has this energy efficiency measure increasing the indoor concentrations, and blue shows it decreasing the indoor concentrations. And that's just because, again, here you are preventing the PM from outdoors coming in. Imagine it's a wildfire scenario, Northwest, and your home is really tightly sealed. So your concentrations are really high outdoors, and you're up in the space, but your home is more well sealed, so less stuff gets in. You go all the way to the right of this, and you're in cleaner conditions outdoors, but you have a lot of indoor sources. Now that tighter building with less infiltration actually increases your indoor concentration. So it points to this interesting interplay between outdoor and indoor PM and how that interacts. So if there's anything you take away from today, whether it be for particulate matter or other atmospheric public health considerations, I hope it's thinking a little bit about that interaction between outdoor and indoors. So in summary, for this slide, which admittedly has a lot of different information on it and colors, the impacts of energy efficiency measures on indoor air quality are partially dependent on outdoor air quality in addition to the in-home emissions. So if you were to translate this to Delhi or another city that has higher outdoor concentration, you have to help how you approach this. There are some studies that were done just looking at a few homes back in Beijing in probably about a decade ago by Bill Nazaroff's group at Berkeley that looked at the changes in home infiltration and sealing and how that actually affected indoor PM concentrations or outdoor ratios. So it does have an impact in other locations, and it can be different than what we're showing here. Okay, so to wrap this up and look at it together. I said we wanted to look at the outdoor effects and the indoor effects. We spent a little bit more time on the indoor stuff today, but we get this huge gain from the reduction in outdoor PM 2.5. This is really like the energy-related PM 2.5. So we've dropped the energy demand for buildings considerably with the cases here. So intermediate, optimistic with carbon pricing. And so we have a huge benefit in reduced premature mortality that's avoided in 2050. We just talked about the complexity of indoors. And so overall, we see a detriment indoors. But this is not for every home, because there's many homes that see a health benefit from the energy efficiency improvements based on this modeling. And so it's those high emission homes, high indoor emission homes that drive the overall effect negative. So those graphs that I showed you before that had the lines across them for HVAC and non-HVAC, we're showing that there's a fraction of homes that see a detriment and see a benefit from this. But overall, the indoor effect offsets this positive outdoor effect, but it's weighted towards a subset of homes and a subset of the population. We look at this on net for those three scenarios, intermediate, optimistic with carbon pricing. We see that we get a net benefit from energy efficiency for avoided premature mortality from PM 2.5. This is stacked on top of all of the benefits that we get from the reduced climate pollutants that we come with dropping that energy. So we get a climate benefit in terms of reduced CO2 emissions, and we get a benefit in terms of improved public health. And that's driven by the large decrease in energy related to pollutant emissions and to some degree some of the homes that have indoor air quality, but we do see some negative effects on indoor air quality overall. That's what I said in summary. And then we wanted to test how the effect of HVAC usage or filtration systems affected this. So if we look at the case where we actually upgraded all homes to have 100% good HVAC systems, so boost that investment up, we can actually increase the health benefits that occur. So basically, if we improve indoor air quality through improved filtration indoors at PM 2.5, we can achieve a larger benefit there. This can be put up as a summary here, where reductions in outdoor emissions yield a net benefit across the entire building stock, and the observed change in indoor air quality due to these energy efficiency improvements really require us to think about improvements to our indoor PM 2.5 emissions, targeted ventilation of those emissions, so better ventilation of cooking emissions, improving the PM 2.5 filtration efficiency, so upgrade your filters, get better efficiency for those of you who can, and then careful consideration of these energy efficiency policies and how we look at ventilation in buildings. And this is yet another time where I wish I had Jordan Peccia on the line as well to make a few comments on that, because it is a really interesting and important topic for how we design building ventilation for human quality of life, well-being, and thinking about a range of pollutants. So we present this today in the paper through the lens of PM 2.5. We include some discussion in the paper about different pollutants that make for indoors and be emitted in various amounts. So that can go through the range of criteria pollutants. We can even start to think about radon in some areas of the country. And certainly have disease transmission indoors, which has nothing to do with this paper, but does come up against the space where we think a lot about building design and filtration and ventilation. So looking at these benefits across the country, the graduate student who was working, the postdoc who was working on this modeled it spatially and looking across various geographic regions. And you can see for the intermediate energy efficiency case, the optimistic one, and then when we put carbon pricing with the optimistic case, where the benefits occur. And these differences come down in many ways to how power is generated or how electricity is generated in various areas of the country. So where we see some of the largest benefits, depending on the case. So carbon pricing is going to have a slightly different effect than on the optimistic case on its own. It's going to change the underlying fuel that we're using for generating power. So if we think about the Midwest and the Northeast here, the types of fuels that we're using for power plants, reducing that demand is going to have a larger effect than West, where there's a higher amount of renewables. So in summary, and then we'll open it up to questions with whatever time we have. The study used the Yale NEMS model coupled with Monte Carlo analysis or quality box model across the entire US housing stock. We see a 6 to 11% reduction in carbon dioxide emissions and a 18 to 25% reduction in outdoor energy-related emissions of PM 2.5. So this is not including other PM 2.5 sources. These reductions are complementary with carbon pricing and takes the pressure off as we're trying to decarbonize electricity going forward. So these building energy efficiency measures provide a huge opportunity, but they require attention to indoor PM 2.5 emissions and improving PM 2.5 filtration and thinking about how we implement these ventilation policies that get at some of the nuances that we're talking about with fresh air exchange and energy recovery. And so in all, the majority of homes see an improvement or a little change to indoor air quality with these energy efficiency improvements, but a subset of homes have increased PM 2.5 concentrations indoors, which affect their overall health effects for indoor air, and we see a net benefit in total outdoors. So with that, we are at 12:50. So I'm happy to take any questions that people have. I have Ken here to answer all the tough ones that I can, so don't want to answer. Thank you so much for your time today and for the invitation for us to present the paper.
So I think we can have two questions.
Okay.
Actually, each student already prepared some questions, so anyone you want to ask?
Hey, could you go back to the projected impact slide? First, if there was a bar on there for, you know, like without the energy, like, where about would it be?
So this is all comparisons to the reference case. So to the kind of current trajectory.
Okay.
So this is the changes that occur on top of whatever we expect to happen in the absence of these scenarios.
I guess we could consider that with it into consideration the outside.
It does. So it doesn't include a distribution of claims saying, you know, across different subsets of the population who would spend like more or less time in their residence. But it does scale for that.
I was wondering if there are plans to kind of extend the study out to different groups. So like looking at I know we're not talking about school systems, but here as well. Primarily interested in so you know, what are there plans to study energy efficiency models, but also including that are there plans to study more factors and other areas?
Yeah, so
Good. So the online audience couldn't hear the students' question. You might.
okay. Yeah, the first question was prior to that was about the for the slide that's up, what the zero line is, and that's the comparison to the reference case. The question that was just posed is how much does, or do we have plans for another study or set of studies looking at gas phase pollutants? And so we include some commentary in the paper about some of the factors that need to be considered. And it does, it comes down to how much the emissions occur indoors versus outdoors. The other, for NOx, you already really got at one of the huge factors there is there is no, there's not a readily available filter that we already have in all the homes that filter NOx with the kind of efficacy that we have with particle filters. So that adds a really interesting thing that makes it so the HVAC system doesn't have as large of effect on that gas phase pollutant. So Ken and I have some things that we're thinking about and working on, although NOx is not one of them at the moment, unless Ken can send me an email later today telling me to start writing. But yes, there's a lot of interesting things here, and yeah, we're just kind of scratching the surface too on thinking about how other pollutants behave with these changes. And Jordan Petchy spends a lot of time thinking about indoor moisture and how that's going to affect microbial activity in the home. So we think about molds and other things. That's an area of interest. I encourage you to try to catch up with Jordan or at least look on that, because that is a really important factor on developmental health. Great.
Yeah, thank you,
All
Greg.
right.
And because we have a class right after us, so we have and thank you everyone for coming out. Thank you again.
Thank you, Ken.